if we make it through this lecture, I'll show you some unpublished results that are just very much at the very the thing we are thinking about at the moment. All right, so this has been a very strong collaboration between my group and Andre Bernevik's group and his postdocs and his students. On my end, this work got started by Stefan and Ilya, who've moved on, and Gian in Andre's group, who's a terrific guy. And now the work, as I'll show you, is being sort of pushed forward by Ben, Malika, Sangjung, and Yonglong. And as I'll show you, we have collaborated quite a bit with Alan MacDonald and his group. All right, so you heard a lot about Majorana fermions, so I'll very quickly go through, tell you what we are trying to do and how this relates to topological superconductivity. So basically, we are trying to create these real fermions. And one way to think about doing that is just basically combining complex fermions that nature has given us, namely electrons and holes. Putting them in the right combination would be a way to create such an excitation in a solid state system. And of course, this is where superconductivity comes in, because as you know, superconductivity mixes electrons and holes. And just when you write down the BCS pairing Hamiltonian, as you all know, the way we diagonalize this Hamiltonian is using Bogoliubov transformation, which is just making combinations of electrons and holes. So these are actually neutral excitations that we make inside the superconductor. And what we are trying to do is make a very special case of these neutral excitations. So in an ordinary superconductor, Bogoliubov excitations come in pairs. There is this redundancy in the BCS Hamiltonian and positive and negative solutions. And the special case we are trying to do is create a very special zero mode in which these all come in pairs, but this one doesn't. And it doesn't in one end of the system, as I'll show you. It always comes in pairs in solid state systems, but spatially delocalized. So I'm sure you, throughout the lectures in this meeting, you've heard a lot about Kitaev chain, which is a starting point in thinking about how you would go about building such a thing in the laboratory. Is very simple. It's so simple that I actually give this as an exam problem in my graduate course for people to find Majoranas in 1.5 hours. And usually people solve it with enough hints, no problem. So remember, this is a Hamiltonian with the hopping term on a chain. And what's special about it is that you just have removed the spin degree of freedom of electrons. So if you want to pair them up, you have to basically pair them up in the p-wave channel. Okay, these are spinless electrons, so the wave function of the electron pairs needs to obey Pauli statistics, and so therefore you cannot put two electrons on the same site if they're spinless, and you end up with p-wave pairing. So this is what we are trying to create in the laboratory. Now, the way Kitaev basically, what the paper is just 3 paragraphs long, which is basically introducing these Majorana operators and showing that this Hamiltonian has basically 2 phases. And the 2 phases are tuned by the parameters of delta, the chemical potential at T, and the phase that is topological basically has a situation in which because of the way the combination of the hopping term and the pairing term enters the Hamiltonian, you end up with a situation where you have a Majorana basically being at the end of the chain, with its partner being on the other end of the system. Okay? So the bulk of these 2 systems would not be different. They would both be gapped. The gap has to close and reopen, as I'll show you an example of in our particular situation. And once the gap goes topological, you end up producing these boundary modes. And they would be at 0 energy, which is what we would be looking for experimentally. So of course, if we actually succeed in doing this, this is quite remarkable, because you have a situation in which quantum information is stored over, if this is an infinitely long system, over distances that are very far apart from one another. So that one thing which is quite amusing and remarkable of if you could encode information into these zero modes. And the other one, undoubtedly, you've heard a lot about, is this braiding opportunity, which is since you have breaking the electron, if you like, into two pairs of Majoranas, being able to move each of the partner around the partner of the other one in pairs creates this situation where you can display non-abelian statistics. So in a sense, these Majoranas are much more exciting than the ones you would find in high energy physics. Okay, so experimentally, the first system that it was proposed to look for this came with the discovery of topological insulators, which basically gave us these surface states that we talked about so much yesterday, in which electron spin and momentum are locked. So this is a natural place in which you can, if you pair on this Fermi surface, spin degree of freedom is no longer important. It's predefined by momentum. So you essentially have this spinless pairing that we talked about. So Lian Fu and Kane propose a lot of different type of structures combining superconductors, magnets, complicated structures that you could create perhaps this Kitaev chain model using topological insulators. This hasn't made it has made some progress, but it hasn't made a whole lot of progress experimentally, where you can say there is a smoking gun for Majoranas in this platform. There are lots of signals that are there are Josephson type experiments people have proposed, but there are no easy experiments that are sort of showing very strong evidence, I would say. I'll show you one of them, which might come towards the end. Now, there is this experiment. I think Sergey was here. He told you all about this experiment, I'm sure, where basically you get rid of your TI, or you create your TI by hand. You take strong spin-orbit coupling nanowire, which gives you Rashba split bands, and you just apply a magnetic field parallel to the wire. So the combination of spin-orbit coupling and Zeeman basically creates this band structure that forward movers and backward movers have specific spins. Again, you're back to creating a spinless Fermi surface, which you pair on. And this is the famous Leo Cohenhoven experiment, which is constructed by basically bringing this nanowire that is proximatized with this superconducting contact and looking at it with a normal region of the same nanowire, which has been depleted with gates underneath here to do a tunneling spectroscopy, very much like STM spectroscopy of the very end of this system. Okay. Now, all devices like this are devices, they're circuits, right? And when you measure IV characteristic and get zero bias peaks, you don't actually know where the signal is really coming from, okay? And this is the point where we got interested in this problem. Is the zero bias peak really coming from the end of the wire? And now you also notice that this sort of zero bias peak comes about when you apply a magnetic field, right? So you have a superconductor and you have a magnetic field. So magnetic field tends to suppress superconductivity. So you always worry whether some of these signals are due to things like Kondo effect. So that's one other idea that could give rise to such zero bias peak, although they have done a lot of checks of that this probably is not the Kondo effect because of the it doesn't split as you vary the magnetic field, although the range of magnetic field is very weak. The other thing that sort of it's great for making technology, but maybe not so great for doing physics, is that these systems all have to be fine-tuned in order to be in the topological phase. Okay, as I'll show you that the system that we're looking at has a disadvantage that is very difficult to tune it, but once you build it and you see pairing in it, is most likely in the topological phase. I'll show you how that comes about. So of course, our motivation was to use the arsenal of techniques. Please interrupt. I don't want this to be a monologue. I've given this talk many times, as you can imagine. I can just go into the auto mode and I could just go through 90 slides. So,
Okay, I can ask.
Yeah.
I should have asked Sergey about it. So why didn't they know where this zero bias
Because every time you make such a device, you have to make an end to do this experiment. So by definition, you have a circuit, you have an end, you see a signal. But it's a circuit. There's no imaging experiment. There is no sort of resolving that. And every time you perturb it, let's say you perturb the gate, you just change the length of the wire. So when the signal goes away, you're like, well, I'm not tunneling to the end anymore. So very difficult. Good? Okay. So our idea, and I'll show you how we came upon this, is sort of actually built on some work that was done before us by Carlo Bineker and Flensburg, was to combine magnetism and superconductivity. Okay. So let me just start with what a single magnetic impurity does to a superconductor. So as you know, superconductivity and magnetism, S-wave superconductivity and magnetism compete. So you can solve a very simple problem in which you put a single magnetic impurity in a superconductor, and you have an exchange interaction between this magnetic impurity and the superconducting condensate. And what that does is basically it creates a excitation inside the gap of the superconductor. So this is kind of like the prelude to the Anderson theorem on the work of, Abrikosov-Gorkov, which is that, as you put magnetic impurities in conventional superconductors, you suppress superconductivity. But if you think about it from the perspective of the excitation spectrum, what happens is that as soon as you put one single impurity in a superconductor, you pull a state out of the continuum and you stick it inside the gap of the superconductor. This is called the Shiba state. Shiba wrote a paper in '69 describing these states. Now, I had worked on these states a long time ago, and I'll show you what we had done. And I knew that if you look at the excitation spectrum of these Shiba states, these are Bogoliubov excitations inside the gap. They're localized near this impurity, as I'll show you. It basically has a transition, which is as you crank up the value of J, there is a crossing point. Okay. And what happens here, I don't have the slides on it, but something very interesting happens here. The parity of the ground state actually changes. Okay. So you have here a situation where the ground state of the system is such that you just have a superconductor, and its ground state is a superconductor. Its first excitation spectrum, first excited state is this one, and then you have the ones above the gap. But when you go over here, what happens is in the ground state you have a state actually occupied and localized in the vicinity of the magnetic impurity. Okay, so the ground state is like all pairs and one broken pair, if you like. Okay, so this was actually known from the 1970s. Okay, so I knew about this, and over lunch I was picking Andre's brain out up about what can we do with this, and I of course knew that we could do an experiment probing this, and I don't know, some of the people here may not have even been born in 1997, I don't know. But back when I had, more hair on my head, we did this experiment where you put magnetic impurities on a surface of a S-wave superconductor. And in this S-wave superconductor, which is niobium, if you look inside the gap of niobium, you see these excitation spectrums having an additional state, okay, inside the gap of the superconductor. So this was the first example where we could actually see the Shiba states with the STM. And they are quite localized in the vicinity of the magnetic impurity. I'll discuss this a little bit more later, but the idea here is that you always think about the coherence length as being the characteristic length scale in a superconductor. But what happens is when you have a localized state, you have this prefactor, which is 1 over KFR. And when you square that, the KF being short in a metal gives you essentially most of the wave function weight being near the impurity. There is a long tail, but most of the wave function weight is near the impurity. And that's why in these are conductance map images, you can see that they are localized around the impurity. So these are gadolinium atoms. Okay. So what will happen if we put this in a chain? Okay, so this was our first question. So the idea came that, okay, this was sort of my experimentalist level idea. which is that, okay, if I have a magnetic impurity, I don't like to put pairs on the site where there's a magnetic impurity, because especially if I have a S-wave superconductor, no unconventional pairing mechanism. But if you have two nearest magnetic impurities and they're pointing there's an angle between them, okay, perhaps I can think about putting my pairs. There's a finite probability that I can put my Cooper pair onto this nearest neighbor site, okay. So this was sort of my plumber level thinking about, maybe this is how you can introduce P-wave pairing. And of course, there are many different descriptions of what I just told you from the band structure perspective, and as we'll go along here. So with this idea in mind, we did the following calculation. This is calculation done by Stefan with a lot of help from Andre. We basically took a chain of magnetic impurities in a spiral pattern, okay, just as a test case. And we essentially computed all the excitation spectrum of this system as a function of the strength of each of these magnetic moments, which is B for just the exchange interaction. And if you just look at the excitation spectrum, you see that as you crank up J, something very similar to a single impurity happens, which is that you get the excitation becomes deeper and deeper as the exchange energy becomes larger. But at one point, what you find is that there is sort of a crossing, just like you found before. But there is a zero energy state that comes about, and it stays at the chemical potential over a range of these values of magnetic moment. Okay, so this came out of, this is a simulation. Okay. And Andre showed Stefan how to compute the parity of the ground state, and he basically found that the parity, the Pfaffian actually changes sign as you go through this transition. Yes? Well, this is what we started. The helical structure is important. As I'll show you, you can compute, for example, from this spectrum, you can compute this size of this gap. So this is our normal gap. This is our topological gap, right? And it turns out that the value of that gap and the range over which this zero energy state survives depends very sensitively on this angle. There is a SWOT of, if you just do a phase diagram of angle versus J, I think we have this in this paper, you'll see there is a sort of a SWOT where this phase, topological phase, is stable. Outside of that, it doesn't appear. Yeah, so this is how we came upon this, and I guess Felix gave a talk here, and they have done a full-blown theory. They have done the sort of analytical theory for all kinds of pitches and everything. The idea is that I think I'm just telling you how we came upon it. I think it's easier if we can now go over to the band structure picture. It will become a little bit more clear. But going back and forth between these two pictures is not even easy for me. I've thought about this for a while. But just these are done numerically. So numerically, we find this sort of swath of space in the parameter space where it's stable. Good? So this calculation could be done in a 2D sort of system on a sort of a number of sites, 100 by 20. And you can do the excitation spectrum and look up what you would see, and you would see that there is a zero energy state. There is a small gap that would be in the bulk of the system if you're in this phase, and that if you looked in real space, you'll find your zero mode are indeed localized to the end, and the first excited state, which I don't have, is throughout the entire chain. Okay, but if you when we wrote this theory paper and sent it to PRL, basically the first referee said, this is a stupid idea, okay, for many reasons. He went on for 2 pages, or she went on for 2 pages. The first, who would bother to do this experiment, okay? This is a very difficult experiment. The second, and this was a good point, how could you possibly get a helical chain of atoms on a surface? Well, it turned out there was an STM group that had used spin polarized STM, as I'll show you how that works. They had actually found this helical spin chain, But no, the referee will have none of it. It's like, this paper is so uninteresting. You know, it's just going to appeal for just to a few people. And it was like one of those things where you go, okay, you know, we're onto something if this really works out. So of course, but this was a good point. I mean, a lot of people criticize this idea because they say, okay, how the hell are you gonna get a kind of magic chain that would have this pitch? But it turned out, actually, you don't need that. You can do it with spin-orbit coupling. And there was actually 2 papers in the literature, not in the 1D system, but in 2D system, where they had considered this idea, combining spin-orbit coupling and ferromagnetism, one by Pete Brower and the other one by Sucheng Zhang. We just didn't know about these papers. But in our chain, it turns out that this becomes very simple. Okay. So when you consider like a piece of iron or a piece of transition metal, when you make them into a nano structure like a chain or a film, exchange interaction is actually quite large. It's like electron volts. Okay, and let's just talk about 1 orbital per atom. Of course, you end up with this situation where you have basically like a half metal. Okay, if the exchange interaction is large. So nobody in their right mind will say that you can get superconductivity on this band structure or proximatize this into superconducting state because this is just all spin polarized. But of course, if your superconductor underneath has spin-orbit coupling, okay, essentially the spin-orbit coupling corrupts, if you like, this beautiful ferromagnetism. And now you can kind of think back to Fu and Kane, or think back to Fu and Kane or the nanowire studies. Basically, what happens is that the spin on this Fermi surface, once you have spin-orbit coupling, at the Fermi surface is no longer, between this point and this point, is no longer parallel anymore. As long as that's not parallel, you can get a component of pairing from a proximatized S-wave superconductor. Does that make sense? Yeah, it tilts a little bit. And this translates into the question about what's the pitch in real space, because that just translates into spin-orbit coupling. And there are some already nice models in which you can do transformation of spin models and go from one picture to another in terms of translating pitch into spin-orbit coupling plus ferromagnetism. And Daniel Loss has written lots of papers on this topic if you're interested in looking it up. So then if you look at this model, and in fact, this was all there in the literature of spin-orbit coupling nanowires. You just had to take the limit in those pictures where the exchange interaction was large. In fact, in one of the papers on that topic, back in some corner of some manuscript, there was an estimate of what would be the size of the P-wave pairing gap, and this you can completely understand, would scale with the spin-orbit coupling and the size of, in their case, Z-man, in our case, J. So, of course, as the spins are very aligned, you're not going to have a great time P-wave pairing, but as your spin-orbit coupling gets very big, this ratio basically gives you a way to make this P-wave superconductor. Yeah?
You're saying that, in this case, effectively, real space, that you get the...
Yeah. It's a question of language. The electrons are moving along. They're hopping between this wire and the underlying superconductor. So you can put the spin-orbit coupling wherever you like. Okay, so, and the electrons near the Fermi energy, if they explore both the wire and the superconductor, if it has spin-orbit coupling, then you can have this effective Hamiltonian. That's the idea. You can make this a little bit more complicated. I'm going to make it a lot more complicated. Let's put in all the d orbitals. So really, like say for iron. And then you can actually compute like what's the topological phase diagram for this system. Okay. And remember, just like any topological phase you've learned about in this conference is all about number of band crossings, right? So if you have an odd number of band crossings, it's going to be all good. You're going to get the topological phase. Here, there are some regions where you will not have right number of, you have even number of band crossing. So what's cool about this system is that once you make J large, okay, you only have one spin species at the Fermi energy. Okay, the other one is the majority band is fully occupied. So you don't have to worry about the downspin anymore. And this basically gives you a system that is almost always topological. Okay? You can get unlucky and get into these phases where, depending on where the chemical potential is and where the who's texting? Okay, so okay. So you'll hear the experiments. You'll hear how we have constructed this. But at the end of the day, to even push this field forward, what I will come back to is building this ideal structure. Okay, okay. And if you could do that, then you can, you can do everything like as is done on paper. Okay, so what do you look for experimentally? Of course, I showed you the simulation, but you can do the simulation for this model as well with different type of calculation. We've, Andre and his group have done many different type of calculation, realistic calculation, model Hamiltonian. I can show you a bunch of different results here. But essentially, you'll be looking for the same thing. You find your chain. If you built it, you create these in-gap states, okay? The magnetic impurity give you in-gap states, but these are now bands of in-gap states. They're Shiba states living inside the host, the host being everything around this chain. This is the host gap. Inside that, you will have some sort of a in-gap states, which will have some sort of a gap. And then at the edges, you will have this zero mode. Okay. So this is what you would go look for experimentally. Okay, so now let's talk about the experiment. How do we actually try to do this? So I showed this yesterday. This is the instrument that actually made these experiments possible. It's an instrument, as I'll show you, that can do a lot of very different things. You can grow things inside. These nanostructures can be self-assembled, fabricated inside without exposure to air. So that's constructed here. They moved into this chamber where the microscope is at the end of a cryostat that can be moved and then plugged into it and tested. In the same instrument, we can also create spin polarized tips. As I'll show you, we actually characterize the magnetism, both ferromagnetism and spin orbit coupling of the structures we're looking at. And there's also a magnetic field for turning on and off the superconductivity and to adjust the magnetic orientation of a magnetic tip. So all of these things have to be brought together to do this experiment. And it's many generation of people have contributed to make these instrumentation possible. So the advantage of this experiment was to work on lead. Lead is the most one of the most well understood superconductors we know of. It's a BCS superconductor, and you can call somebody and get a lead crystal. Don't eat it, but you can put it inside this instrument and bombard it with argon atoms and anneal it, and it can basically make a beautiful crystalline surface. Okay, and we picked the lead 110 surface because when you cut lead in this orientation, it has these natural rows. Okay, and we were following the work of some other people who used iridium in a special orientation where it had also rows. And our idea, as I'll show you, which worked, was to use this as a template to create one-dimensional structures. Okay. So yes, lead is very well understood BCS superconductor. And there was a question about energy resolution yesterday. This is how you calibrate your energy resolution in an STM setup. You take a BCS superconductor, and this setup has a temperature of 1.4 Kelvin. I'll show you some lower temperature measurements a little later today. And you can basically do the tunneling density of states, measure the tunneling conductance, the IDV as a function of voltage, see the BCS gap. And these bumps and wiggles you see out here are actually due to electron-phonon coupling features that's been known since the 1960s. This is actually how you know this is a strong coupling BCS superconductor. And the analysis of these features in the 60s was actually the thing that allowed us to really quantitatively be able to pin down BCS pairing for electron-phonon superconductors. You can back out from these features the spectrum of the phonon mediating pairing. So of course, lead has strong spin orbit because it's a heavy element, but let's hold that thought, or I actually show you some very nice experimental evidence for that. Okay, so we got very fortunate, which is we found a way to make chains. So you take this surface, this is a very large area of the surface, all of these shaded regions with different colors are basically different terraces at different height. And you take this sample, inside the instrument you just evaporate iron on the surface from an evaporator, from an e-beam evaporator, and you anneal it. Before you anneal it, you get these blobs only, but after you anneal it, you see that there's some structures basically being created with the blob in the middle. Okay. I'm sorry? Nature gives you terraces. It's not going to be absolutely flat. No, we don't build them by hand. We just take the crystal. Once we check that it's clean, you evaporate iron and you anneal it, and you find them everywhere on different terraces, different region of the sample. So in one experiment, if you like, if all goes well, you have many, many chains to study at the same time. Yes? Yeah, that's what it looks like. Basically, the lead is this anisotropic surface. And actually, the structure of these chains are a little bit more complicated than I'll show you than just single atom chains. They appear to be single atom in this direction. Okay, and so this is another thing about STM images. When you have a very small structure like a single atom on the surface, like this is a single atom on the surface, what you end up doing is you're actually imaging your tip with your sample. Okay, and basically what we see is that the width of this chain is consistent with the width of a single atom being imaged when we deposit just single atoms at low temperature on the surface. And you can kind of see that the center of this chain, I'll show you more data a little bit later. Actually, is it here? Yes. So you can look at the details. You can really zoom in and look at the details. And we can see that the center of this peak, this is a cut this way. It's in between kind of two corrugations of the lead. But now this becomes the nitty-gritty detail. Lead actually doesn't fit with iron. They have different lattice structures. So of course it looks beautiful when you look at it as far away. But if you zoom in, you start to see picometer modulations, okay, on top of this structure of this chain. And if you go nearby, you see even the lead. I don't know if this is coming out or not. This is a cut taken this way. You can see that it sort of strains the lead to fit in. Okay, and so question. So these are actually very detailed information, and this is kind of like, if you want to think about it, this is like determined by the band structure of the lead system you have and the iron. Then these are things that you should be able to actually calculate if you know the structure of what you have made. DFT calculation is very good at capturing these details of STM images. And this is where we started working with Alan and his student Ha to figure out, his postdoc Ha, to figure out what have we built. Okay. See, STM gives you some structural information, but it's all filtered through the fact that we are measuring electronic behavior. So we had a few clues, and that the distance between what would be the atoms is not what you get in iron. It's actually a little bit larger than iron, and it's not the same as what you get in lead. And through that, and through the height measurements and all these details that are very reproducible, if you make measurements, let's say, these are measurements done looking at density of state, let's say, integrated up to 1 electron volt, very large. You can capture all of these features if you make a structure that looks like this. Okay? So what does this look like? It's basically a zigzag structure of iron, where the iron atoms are just sitting as they would sit inside a iron crystal. Okay, and we believe that this is the most likely structure of this chain we have built. Okay. For some of the claims I'm going to show you, that some of this doesn't matter, but it's important to understand what you have done, because the fact that we think the distance between the iron atoms is about the distance of that in bulk makes you feel comfortable that this chain would be ferromagnetic, as I'll show you we have found. Okay? It turns out if you do a calculation, if you stretch the iron chain, you'll find that at some point it likes to be antiferromagnetic. So there are all these details that you really need to understand. Okay, so this zigzag chain, you can model it. You can put iron in a zigzag chain and compute what its band structure would be. Okay? So these are all the things that are under the hood of our paper that I don't usually get to show. But these are kind of checks you can make. You can take this and band structure and say, is this going to give me a topological superconductor if I have spin-orbit coupling? Okay? And the answer is yes, provided that the exchange interaction in iron is about 2 electron volts, which we believe there are many measurements and calculation which tells you that's what it is, and provided we hadn't screwed up where the chemical potential is in this system by about half an electron volt. Okay. Now from this calculation, which is based on that structure, you can compute what the density of state of this chain should look like. Okay? This has nothing to do with superconductivity. This has to do with the fact that what's the electronic structure of this chain? You have this band structure, compute the density of state of this band structure. You see there's a lot of bands here. There's a band hole singularity there. And that translates into the density of state that looks like this. Okay? And then you can go to the experiment and you can look to see if you see anything like it. And it looks like we do. So this is now high energy physics, 1 electron volt. This is the tight binding model of this chain structure. It will predict this sort of Van Hoff singularities. And we see things that are roughly looks the same as what we expect from this tight binding model. So we made a measurement of the structure. We put the measurement of the structure into a theory. We got out the density of state. It matches the experiment. At least there is some consistency. Okay, these are just some details. But now, what's the magnetic structure of this chain? Yes? Well, just the fact that you have this 2-peak structure. This is those of us who do STM will tell you, if you see something like this very reproducibly, you'll say, oh, where is this coming from? This is coming from something that, some sort of a band structure effect of your system you have built. Oh, that's the measurement on the substrate. So you take the tip and you make a measurement of what the density of state looks like on the lead. It looks actually like this. And it turns out that you can actually understand why it looks like this. There is some band coming on as you cross the chemical potential. And this is the measurement of using the same tip, measuring the chain. Chain on top of that. This one was done like this, but you can also make the calculation more sophisticated, and it ends up showing something very similar to this. But the problem is this, okay, this is an incommensurate structure. So you can't ask a theorist in good faith for them to, spend their lives calculate what the band structure would be. Very difficult, right? But once I put it like this, it's very easy, right? That's the technical difficulty. Good questions. Yes? Don't. So if those are all questions that are. So there are some things that the images, these are very sensitive. The height of these peaks and so on in the images are very sensitive to where you put the chemical potential, because it will involve charge transfer between the lead and the iron, and it will change the density of state of your system and the features in the. We don't know very precisely, but we have an idea.
Probably.
Yeah, but I'm just telling you what we know. Okay, so let's look at how we do this with magnetism. I'm going to show you actually quite a lot of magnetic measurements. So, this is pioneered by a number of different STM groups, mostly in Europe, where you take your STM tip and you coat it with some sort of a magnetic structure, which gives you say a ferromagnetic end, or it could be even an anti-ferromagnet. I'll show you later. But it has some region at the end which has a magnetization, which is well defined. And the problem with these experiments are that there's a lot of things in the literature which will give you a recipe of how to make these tips, and they'll say, oh, it'll point this way or it'll point that way, and we find that most of that is very hard to believe. But what is nice in this instrument is we have a vector field, and we can use this vector field to manipulate the orientation of this spin, magnetization of this tip, and we have other types of samples which we can use as a test structure. Besides the one I'm going to show you, to learn things about those tips. And we have done a lot of things like that. Okay. So you use these tips. These are actually chromium tips with some iron at the end, which we create by basically poking the chromium tip into the blobs. And they make very stable tips that can be actually switched at about a quarter of Tesla. So what happens is you take this tip and you bring it over, sorry, these two pictures should be swapped. You bring it over the chain. So I've taken a three-dimensional picture of the chain here, and I have colored it with the height of the tunneling density of state measured at 30 millieV between the chain and the tip as a function of applying a perpendicular magnetic field to this structure. Okay? This is an extremely painful experiment because you have to make sure the tip doesn't change as you sweep the magnetic field. And unfortunately, to make very high resolution measurement, you can't sweep the magnetic field while you make the measurement. You have to turn the field off, make a measurement, turn the field back on, and repeat it, see this hysteresis. And of course, to make sure that the tip didn't change, do it again. And you have to, everything has to stay the same for 3 weeks. That's how long it takes to take this kind of data. It's a very painful experiment. But it's been reproduced many times in our lab, so we are very confident of it. And so you can see it's like a classic example of tunneling between two ferromagnets. When the two are aligned, it's high signal. It's like GMR, giant magnetic resistance. When one is down, the other one is up, is low. And then you have hysteresis having to do with the fact that it takes a field to sort of switch one of the magnets. So you can do this on many, many chains. All right, so you go around the surface, find this chain, that chain. So what is done in these pictures is the topography has been colored by the size of the spin polarized signal. Okay? So the magnetism is not completely uniform, as you might say, looking at these pictures, for example. Okay, it's not completely uniform. But if you look very carefully at these, you notice that basically there is no, as I will show you, I think a little bit more detail, there is no shift in any kind of period of the magnetism. So if you have a high signal, remember we are always convolving topography, everything into this measurement. So if you have a high signal in the conductance, if you flip the magnetization, that high signal just becomes low. If it has a peak in space, it doesn't shift in space, such that you would have, let's say, an antiferromagnet. Okay. So we're looking at, say, states at like 100 millivolts, okay, and they show this behavior, okay, and that's a good question. Now I'll show you that we also see evidence of spin orbit, but very hard to measure that on top of this signal, it seems, okay. But what's nice here is that you can see many different chains behaving the same, okay. This is where we found the surprise. So of course, when they're doing the experiment on the chain, they go off the chain and do the same experiment just to see what it would show you. So lead, of course, is not magnetic, but you have a magnetic tip. So you would expect to see nothing as you vary the magnetization of the tip relative to the surface. Well, but there is spin-orbit coupling. So here's a signal of tunneling between the green, between these tips that switch at a quarter of Tesla and the substrate. And you can see that when I'm at positive 1 Tesla or negative 1 Tesla, the signal is the same. That's good. The signal is symmetric. That's good because lead is not magnetic. But you notice that the signal is higher when the field is lower and highest at 0. So essentially what we think is going on here is you have a tip and you have a surface. The electrons in the surface are experiencing Rashba terms, which basically forces the electron to spin to be parallel to the surface. So if I take my tip and have it be perpendicular to the surface, its magnetization, the tunneling goes down. As I let it be at whatever angle it wants to be, this tunneling signal is largest. Okay? Does that make sense? So this actually, we thought we discovered this. We're very excited for about, 2 hours. And we found that no, actually somebody had seen this effect before, which is was just not done with STM. They had basically made iron. They put gallium arsenide and gold. Now gallium arsenide has spin-orbit coupling, and they're tunneling through gallium arsenide, and they use a magnetic field to reorient the magnetization of the iron film. And this allows them basically to see, the signals look almost identical. And this allows them to actually measure quantitatively evidence of spin-orbit coupling in gallium arsenide. So it's spin-dependent tunneling through because of spin-orbit coupling. Okay? So it looks like we got everything. We got, yes? This one? Look at, yeah, here. It depends on the angle of the tip. So we have done a lot of work trying to model this. So it depends what you put as the easy axis, hard axis, and isotropy of the tip, and how large it is compared to the field you apply. And essentially, these little features can all change around if you change those magnitudes of easy and hard axis. And a lot of the tips we make, all these little details will shift around a little bit. Okay, and the challenge actually in these experiments is that often you find the tip that should be magnetic, should have magnetic contrast, and it has no contrast. So you have to really do these field measurements to really, you have to have a test structure. And our test structure is actually cobalt on copper, which make these domains that are up or down. It's just like little bits you can read. You can test all these on it. Yes? Well, it looks like, I think if you go look at the signal on the chain carefully, it looks like the two kind of add together. Okay, it looks like you can, we have something I think in the paper where you subtract one from the other. When you're on the chain, it appears that this signal is also there. It's of different magnitude. Also, remember, when you measure experiments on the chain, your tip is a little further away from the substrate. But it looks like both signals are playing a role if you look carefully at this data. Well, how does it change our interpretation? Interpretation is basically when we are on the chain, we have this very strong ferromagnetic behavior. And when you're on the lead, you don't see that. That's good. But you see this very strong spin-orbit coupling term. Now, when we do our model, you can put your spin-orbit coupling term into the lead sites or on the iron sites. And you can do that. And that will create for you also a topological phase. It just matters what the hybridization is between all these states. The fact that the superconductor have spin-orbit coupling in it, that's enough in the model calculation for you to get you in the right phase diagram. Well, I can go look. I think there are analysis of this data where we can look at subtracting or we can see there is some remnants of the spin-orbit coupling signal when you're on the chain. It's not as strong, but it's sort of like, it looks like a tilted, not tilted. There are all these little features that come in that you can try to convince yourself that maybe there are two pieces there. But these are all like small signals.
So in the theory calculation of a spiral,
So you can do different calculations. You can do a spiral. You can also do a ferromagnet, and you can just put spin orbit coupling in the superconductor. Yes, but it depends on the magnitude of alpha, J, and your superconducting host. If it's very, very small, alpha is very, very small, your gap is going to be very small. You're not going to induce much superconductivity. Right. I mean, it also depends on the number of bands. If you have a lot of bands, you might end up getting unlucky. There are regions that you don't end up with superconducting. Okay, so now we can do the spectroscopy on the chain and look at effect of superconductivity. So as you go just slightly off of these chains, you basically recover the BCS gap of lead. And as you climb onto the chain, you see a lot of different things happening. Okay, I'll show you all this detail, all of this in great detail as we go along here. So this is an experiment at 1.4 Kelvin, and in the middle of the chain, you can clearly see that there is a suppression of the density of state relative to the background. And basically, you can think of this, what you're seeing here, as basically the lead gap. And inside that lead gap, you have this band of Shiba states inside that lead gap, which are forming inside the system. And this kind of behavior can be seen sort of throughout the chain. There are variations, as I'll show you as we go along here. But the key thing we observe is that as you go to the end of the chain on either side, so here at this end or at the other end of the chain, you see this very clear zero bias peak in the middle of the signal, the forest of Shiba states, basically coming out just at the very end of the chain. Now let me show you that signal in a slightly different way. So what this is basically distance this way, energy this way, and the colors basically represents the height of the signal. So this peak corresponds to this red line here. Okay? And this dot you see here, this is our zero bias peak at this end of the chain and the other end of the chain. Now, what I like about showing the data like this is that you can kind of see that as you go to the end of the chain, these states, these bulk Shiba band states, they respond to the fact that you're getting to the end of the chain. Okay? But this zero bias peak, if you plot the data like this, you can see that it kind of comes almost out of nowhere. Okay? And shows up at the end of your system. Okay? Now, what you can do with the STM is now you can do spectroscopic imaging, like we discussed yesterday. You just dial some energy and look at what the electrons are doing at that energy, right? So these are all states inside the lead gap, okay? So you can see that this is the band of Shiba states, if you like. They show some sort of a modulation throughout the chain, okay? And these modulations could be coming from sort of finite size effect. It could come from structural features. We haven't completely analyzed this. But then if you look at the zero energy, this was our very initial data, which was published a couple of years ago, is that you can see this zero energy mode localized to the very end. And this is basically seen, on now hundreds of chains. Okay. Okay. So maybe this is just the Kondo effect. This one? No, this is with just normal tip. Yeah, thanks. Yeah, I'm sorry. We always switch back and forth between these different tips. We can change the tip out. And yeah, so when we use a magnetic tip, I'll get into magnetic tip measurement some more in a little bit. If you use a magnetic tip, the tips I first showed you, they are sort of strongly magnetic, so you could actually affect the superconductivity under them. That's why we don't use them. But there are ways to get around that too. Well, okay, so this is what I showed you. So let's just review it. There. So we've measured many, many chains with their magnetic structure. They look the same. Yes, but these are, you know, in one sample there are, you know, as much patience as you have to look around, there are chains. Okay? Then this is the sample, and the substrate is lead, so that doesn't change. So these results doesn't change if I take my tip out and put another tip in there. Okay? So then I use a normal tip. In fact, I'll show you later, we even use ferromagnetic tips to do these experiments. And then we'd use the non-magnetic tip to do these measurements. But if your tip is weakly magnetic, actually, you can do both experiments at the same time. I'll show you those in a little later. But this signal, this particular data was taken with a normal tip. But it's reproducible. You can measure, statistically, you can measure more and more chains. And, you know, statistically. It's just there. Structurally, they're all the same. I mean, there are about 10% of them that look like they have blobs at the end or their structure is messed up, and we stay away from those. The ones that structurally look the same, they're like about 80% of the wires that we make, and all these measurements look the same on them. Okay. Yeah, let's yeah. So they're very short, and this doesn't depend on the tip. Well, it does depend on the tip. We actually now resolve even sharper features, which I'll get into a little later. But that's a question I'm going to address in a second. This one? This one? This one? This one? This is the Shiba states in the middle of the gap. Okay, so you can think about these Shiba bands inside the gap of lead, and you know, basically there is a gap in here. We can discuss that more in detail, which is very hard to resolve. It's small energy scales, but that's the other gap. That's a gap in the spectrum. Which these experiments were done at 1.4 Kelvin. Yes.
Okay, so that's basically my question. Like, is there a way to plug it in?
Yeah, let's discuss that as we go along. That's a good question. I will have to show you a bunch of different data. So that's also the question. It's also a question of energy resolution. So these initial experiments were at 1.4 Kelvin. Yes. Where did the coherence peaks go? They basically, once you go inside these chains, you can think about these Shiba peaks as kind of like your new coherence peaks, if you like. They're actually asymmetric in magnitude, not so much in energy. And I'll show you more details of this at lower temperature. So the way to think about these magnetic structures is that they're not just magnetic impurities. They're also different atoms. Okay, so when you solve, say, a impurity problem in a superconductor, you have to also add a scalar potential, which will make the electron hole asymmetric. And the band structure can be electron hole asymmetric, and that gives you additional electron hole symmetry. And that's also seen on single impurities. It's not specific to these chains. Dan. The green ones? Oh, right here. There. Yeah. That's right. Yeah, so I'm going to show you what, that was one of the first questions. Let's see, is that next? Okay, so let me first show you this, and then we go to that. Okay, so first thing is everything I showed you depends on superconductivity. So I can just apply 100 millitesla, which this is a lead crystal underneath. 100 millitesla will kill superconductivity in lead, and everything goes away. Okay, so this is kind of important, because if I have some sort of a normal metal region, if you like, I've created, if I just apply 100 millitesla, it shouldn't care. Okay, so this is actual data. It's very boring, but you know, these lines are basically flat in this region. Okay, so our zero bias peak really requires superconductivity. Okay, so this is actually very good if you want to claim. It's a Bogoliubov state, no doubt about it. You know, the question is it the true Majorana at zero energy? Okay. Okay, well, in principle, it can. Okay, good. So you're asking all the right questions. So I'll show you how we're. So keep that in mind as I go forward, and we have some other tricks up our sleeves that I'm going to show you. But let me tell you that well, at least the good news is that all the experiments I showed you are basically reproduced by other people. Okay, so this is a group in Basel. They grew the wire exactly the same way we did. They find zero bias peak. There is something very strange about their data. They even can resolve it at 4.2 Kelvin. But never mind that. The best experiment is this one. The better experiment is this one. Is that was done by in Berlin by Katharina Franke's group. She used a superconducting tip to study these chains. And now a superconducting tip gives you, has this Van Hoff singularity of the BCS density of state. It gives you a little bit more resolution. And now your zero bias peak should not appear at 0. It should appear at the gap of your tip. Because you're kind of measuring your sample with a tip that has a gap. And they indeed see this zero bias peak. We also did this experiment. I can show you our measurements too. And this goes to the question you ask. Where is the P wave gap here? How large is it? Okay. And I'm going to give you some feeling for that as we go along here. So they basically said in this paper, they see a zero bias peak, and the next peak they resolve is at 80 microvolts. Okay. So they say, well, maybe that's the P wave gap. That's the first excited state we see, besides the zero bias peak. So you can read this paper. It's published in PR. Okay, so in these experiments, it's not so bad because you can take your same tip and move it away from this chain and tunnel into clean lead and analyze the SIS tunneling. Yes, they can. Yes, and the tips are not as good as what you would think, because when you do that analysis, the size of the 2 delta peaks you get, which you're familiar with, are going to be broader. These tips are not as great as people advertise them to be, but you can characterize them. We have done a lot of experiments with superconducting tips, which was in the original paper, which I'm not going to talk about, because for the reason you just said, we don't actually fully understand these tips. We find that you get better resolution if you just use normal tips and just go to lower temperatures. Okay, a lot of great questions. So let's see if I can address them, at least some of them, as we go along. First, let's talk about the size of this. So when this paper got published, people came out, with their boxing gloves, or actually some without even their boxing gloves, basically going after us one after another. So the first one was the length scale. Okay, why is this Majorana living on such a short length scale? If you listen to Felix or other people or Sergey, you think about a one-dimensional system, right? You induce a P wave gap. The size of the Majorana is the size of the coherence length of this P wave gap, which is tiny, right? And so if you do your VF over delta calculation for what the size of the coherence length should be in this 1D system, you will get a micron. And in the nanowire experiments, that length is a micron. So what is happening in this experiment? So the first thing we thought of was, okay, look, when we do our calculation, we look at these low-lying excitation, we always see a very short length scale. And we kind of appeal to this very simple argument at the beginning that, look, there is the size of whatever state you create inside the superconductor, sure, is controlled by the coherence length. But there is this Fermi wavelength, which in semiconductors is very, very large, but here is very, very short. And so if you square this, and we had done this before, you get something like 10 angstroms over which most of the wave function weight would live. So then came the big guns, Glassman and Van Oppen. They're like, no. This is actually much more interesting than what you say, because essentially what you've created is a very strange band structure. So let me try to sort of give you the experimental version and then show you some plots. So the bands of this chain are very strange. You put magnetic impurities. It creates in-gap states, but the in-gap states are not really part of the iron atoms, they're really property of the superconductor. So what does that mean? The electron actually hops on and off the superconductor to create these Shiba states along this chain. So it's kind of like a very slow line. You know, when you're traveling along this line, when you want to tunnel from one side to the next, you first go to the superconductor and then go to the next side. Okay? So basically, they propose that what's happening here is there is a renormalization of the Fermi velocity of these Shiba states. They're actually like creating heavy fermion bands in this narrow band gap. So here, actually, Jan we checked it out in our calculation to try to understand their picture. So I'll show you what this looks like. So imagine these are now the states of this chain, just projected along the momentum along the chain, okay, computed. And this is the gap of the superconductor. The gap of the superconductor is very narrow. So that all these Shiba states have to be stuffed inside this superconducting gap of, let's say, 1 millivolt or 2 millivolts for lead. Okay? So what happens is that when you couple a single band of magnetic atoms with the superconductor with spin orbit coupling, you create these Shiba states. And this is what their structure looks like inside the superconducting gap. Okay? And as you adjust so with these calculations adjust the coupling between the chain over the hopping along the chain. As the coupling adjusted, basically the band structure of this Shiba state changes, which is not so surprising, right? But what you see here is basically the structure of this band is a band stuffed within 0.5 millivolt. It's a very, very heavy band. It's almost flat. Okay. So their idea is that the characteristic length scale, when you think about the Fermi length scale or Fermi velocity for this system, is you got to think about this band as having the characteristic Fermi velocity, and this band is extremely heavy. So the answer to your question is what determines the length scale over which we see things appears to be with the fact that here the Shiba states are very heavy. The Fermi velocity is very slow. So you take VF over delta, you get 10 angstrom or 15 angstrom, which is of the order of the experiment. So this is our current understanding of the length scale. And then the groups that were opposed to this idea immediately published a paper saying, no. This is all correct. We predicted it before. Okay, so the next criticism is question. Yes? This is for a chain. What I showed you before was for a single impurity. So a single impurity is a function of the size of the impurity interaction. So I'm not sure I understand the question. Okay. Well, if he comes to you, tell me. So you can imagine to create a chain and tune it to have some unlucky situation where you have a zero energy Shiba state. Is that what you're asking? It is potentially possible. Okay. So this goes to the question is how can you distinguish between the Shiba state and an unlucky Shiba state at zero and a Majorana? So hopefully I'll get to that. So before I get to that, I have to show you two other things. Okay, these are experiments that are just being submitted. So first was, maybe this is not even a zero bias peak. If you cooled it down, it just will split. Okay, and you just don't have the resolution to see it at 1 Kelvin. So we repeated these experiments in another instrument, which gets to millikelvin. The electron temperature gets to 200 millikelvin. And you can check the electron temperature by tunneling into the lead crystal underneath. And in fact, the electron temperature and the resolution is so good that you can actually resolve that lead actually has two gaps. And these are the two gaps of lead that was actually discovered before in many, many years ago. For a while, we thought we were making a mistake, but actually this is what you expect. So the fit that you see here is with the electron temperature of 200 millikelvin. So now, when we go to these very low temperatures and repeat the same experiment, and people were asking about, what happens to the, the Shiba states. So the Shiba states actually are made out of a lot of very sharp features, okay? And there is a forest of peaks here. But again, we resolve a zero bias peak at the very end of the chain, which I'll show you this special structure in a minute, okay? And with this experiment, we can put a bound first on what's the splitting of this peak. And the splitting of this peak has to be less than 45 microelectron volts, okay? So this puts a bound on how true is our Majorana. And so this is sort of the first thing you read off of this curve. The second thing you read off of this curve is where is the second peak? Where is the second excitation? So remember, the width of these peaks here is all coming from the thermal broadening of the experiment. Even though you're at 200 millikelvin, you will still have some finite energy broadening. And this is the second peak, and it's sitting at around 150 micro eV, okay? So again, I don't know whether this is a P-wave gap, but this is a feature that we resolve throughout the chain in the system. So let me show you the data in a slightly different. This is the same data I just showed you, okay? And this is just showing you the cut as I come onto the chain. So this is your zero bias peak. You notice that we can resolve other end states as well. And these will all broaden into one Shiba band, but now we can resolve every single one of them, okay? Okay, so what's going on here? Why do we have a forest of peaks here? Well, the way we understand this forest of peaks is because the band structure of what we have made is rather complicated, as I showed you. Okay, so it's not just a linear chain. So if you take this zigzag chain and do a calculation of what you would expect to see, you would see a lot of, and also if you make it a finite size, you would see a lot of features inside the gap of lead, okay? And what's interesting about these calculations is if you broaden them to basically the temperature of the experiment, at about 200 millikelvin, you find that qualitatively they look the same. You can very easily resolve this zero bias peak from the Majorana state, but the gap that should be something background here, once you look at the thermal broadening, is very, very difficult to see it in this measurement at that level, because just the broadening is of the order of the gap that we see. Maybe about a factor of 1.5 bigger gap, but it's of the same order.
When we're looking at zero bias peak in this experiment,
Okay, great question. So there is a prediction that the size of this peak would be 2e squared over h if you have the situation where the temperature of the experiment is lower in energy scale as compared to the coupling between your probe and the Majorana. Does that make sense? So you have an energy scale for coupling, you have a temperature at which you're doing the experiment. So in the STM, what you can do is you can vary the coupling by bringing a tip closer and further from the sample. So we can get the size of this peak to be of the order of 0.5 or 0.4 e squared over h. But if you go closer than that, we destroy the sample. Okay? So we believe even at 200 millikelvin, we are in the regime where we are dominated by thermal broadening, where the coupling to the system is very weak still. The temperature is still too high to get. That prediction is very much like a clean, very low temperature prediction. And incidentally, the most recent experiment in the nanowires, which is done by Charlie Marcus, maybe did Sergey talk about that? They also see 0.3 or 0.4 e squared over h, even in the most cleanest nanowire. And what's interesting is that the one measure that you have here is the size of this peak relative to the background. The data I showed you at 1.4 Kelvin, that peak, if you remember, was way down there compared to the normal state background. Now, routinely at these low temperature, we start to see these peaks get up, not quite, but almost a factor of 2 above the normal state background.
The analogy to the
Well, I think we don't completely understand these issues of background in these systems and how they affect this prediction of E squared over H and so on. They all have backgrounds. So you see, there is a background here from all these Shiba states. And how this affects this prediction, I just don't know. That prediction is when you have no poisoning, lots of things have to be perfect.
So the superconducting gap is
Not in 1D. In 1D, it would just be a full gap. In 2D, you can have, you can have nodal directions. But think of it like a P plus IP. In 1D, it's fully gapped.
so 1D should be like
Yeah, so it's fully gapped. It's like, think about it. There's no nodal direction because it's one-dimensional.
how do you put this?
Edge modes. That Andreev state at the edges, Majorana states at the end. That's the only distinction you have. Or how it responds to disorder. But the disorder make it have in-gap states. Or you make some sort of a pi junction and measure the pi phase shift. Those are the different ways to distinguish. Okay. With the higher resolution measurement, we start to see, yes? Yeah. We can do, these experiments are very reproducible from chain to chain, this end to that end. Very reproducible. We can't do it simultaneously, you know that, right? Yes, the zero mode is always there. And the other thing we discovered at this lower temperature with higher resolution is we discovered something else, which is that our peak, this blob, this Majorana feature at the end, actually has structure. Okay, so this was actually very surprising. So, and this actually explains a lot about the differences between some of the experiments. So, in order to get the, let me see if I have it here. Yeah. If you do a cut of the zero energy strength through this end of the chain, you'll see that the zero energy actually is highest when you're not exactly in the middle of the chain, but tunneling on the side of the chain and on either side of this. So this asymmetry between these two sides that you see in this double eye is actually tip dependent. The tip has to be very sharp and you can have a slight asymmetry. This side could be higher, that side could be higher. But with very sharp tips, you begin to resolve that this end state actually has sort of features that look like, in order to tunnel into it, you want to be not exactly in the middle of the chain, but slightly on the side. So this took us a little bit of time to figure out. But the way you understand this is you have to go back and think about how STM actually operates. The way it operates is when it comes over this chain, you have to actually pull the tip back. Okay? And what you're doing all the time is you're normalizing everything you measure to the normal density of state, right? So you integrate. So when you take an STM image, you dial your voltage to some value, and this between 0, the Fermi energy, and that value, you integrate the density of states at every location, and that determines the height of your tip. And the density of state on the iron side and the lead sides are different, and so is the structure. So there is this tip trajectory that you have, which actually changes the way you couple to these Majorana states. Okay? So this turns out to be a feature of all end states in this system. I showed you that we see end states at other energies. They also show this double eye feature. And the way we understand that is basically because when you do this STM experiment, you're always normalizing everything to the total tunneling current in the system. And this normalization of the tunneling current is determined by the normal state density of states of, say, the iron sites and the lead sites. And basically, you have a difference in the density of states between the host and the iron chain. And this can give rise to this double eye feature in the signal. It's a combination of how the STM tip basically normalizes everything you measure. But the conclusion of this study was the following, that a large part of what we talk about as the Majorana wave function actually lives inside the superconductor. Okay? It's not just living inside this chain at the very end. It's actually a property of the superconductor. So this gave us the idea for another experiment. So why don't we bury the chain? Yes? So the Shiba states don't seem to show it, but the end states at other energies seems to show this double eye feature. But you're right, we don't see it in the Shiba states so much. I have to go back and take a look. Maybe some of the other ones do. So the Shiba states, in these measurements, you also see that as you go to higher energies, the states leak more into the superconductor. So they're not just localized on the chain, they're actually kind of like, you can even see more of them on the side of the chain. So we see features like that. So this gave us an idea for another experiment. Why don't we take the iron chain and bury it with some lead on top? Okay? Okay, this is not a perfect experiment, but what's nice about this experiment is that now we have lead covering the sample, and we can't make the lead perfectly ordered atomically. We have to anneal the surface, and if you anneal the surface too much, basically we destroyed the chain underneath. Okay, so that's a little bit of a detail. And you might say, well, how do you know where the wire is? Right, so this is the topography. So what we do is we basically look inside the gap of lead. It's kind of like reading a tunnel underneath the ground. You can kind of see that the wire is underneath, and it's creating in-gap states that you can image by looking at this energy dependence map. So this is kind of what we have. And what's really neat about this experiment is, again, you can resolve the zero bias peak, okay, very clearly at the end of the chains. And there are some blobs in the middle of this chain which also gives you sort of in-gap states which are at zero bias. But you can kind of see one thing, which is that, we start to affect all of this Shiba state background when we make measurements on top of this lead sample. And you notice that they became symmetric, okay, electron hole symmetric, which is what you expect to see if you tunnel into the in-gap state of a superconductor. And there is no, this is all lead everywhere. But the zero bias peak is still there at the end of the chain. So this is done at 1.4 Kelvin, not at the lowest temperature. One monolayer. Well, so we are not tunneling into the iron sites anymore. We're tunneling into a lead monolayer, and lead monolayer on top of lead with some iron underneath it. It really looks like we are recovering sort of the full integrity of the superconductivity in lead, even though it's affected by the presence of the iron chain underneath it, but it's most affected by the zero bias peak. So so our picture is something like this. You create in-gap states in the superconductor, okay? And you don't have to measure them on the iron side. You can measure them on the superconductor nearby. In the geometry that we have where it's like this, it's very hard to assess what happens nearby because the STM always does this. But this experiment kind of covers everything up, and you can kind of see that there is this decay of these in-gap states into the lead around it, including the zero bias peak.
Does that overgrow also?
I don't think it does, because that idea is just have to do with the fact that you're talking about the in-gap states being created by the topping between the iron site back and forth between iron and lead. The calculation that Felix and Glassman did is like a bulk sort of calculation. It's not like they take a chain inside the 3D bulk. Okay, I'm officially out of time almost. So can I talk for another 15 minutes? Where are the organizers? Now I can show you stuff that's completely raw. Okay. Now this is okay. This is what we are working on right now. Okay. So there was a question, many questions, and of course we had the same question as to what are there other signatures that are unique to Majorana. So we start thinking about the spin, and so if you write down, when you create your Majorana, there is something very strange about it, which is that, unlike a Bogoliubov excitation, when you write electron on holes and switch your spin index, the Majorana electron hole part has to have the same spin index. Otherwise, the conjugate of this operator would not be equal to itself. Okay, so we're talking about the state of definite spin. Okay, so this distinction's got us thinking whether there is a way in which we can distinguish a Bogoliubov state at zero energy and a Majorana at zero energy. Because if you write a Bogoliubov state at zero energy, because they come in pairs, essentially the both spins are present in the description of that state. Both spin up and spin down. So this idea, of course, has been thought about a lot by theorists. This is a calculation, I think one of the first ones where they proposed in the nanowires, if you could measure the spin texture of the system, the end states will have a definite spin orientation, spin polarization. There's a paper by a number of people, including Patrick Lee, which looks at Andreev reflections from the end of these systems and using these as a way of making spin polarized end states, currents. And there is a theoretical work looking at, remember, another way to make Majoranas is this TI Leon Fu Kane platform with topological insulator superconductivity and creating Majoranas in the vortex core. And there is actually a very recent paper which looks at spin polarized tunneling into the end of this, inside these cores, claiming that there is some spin contrast. Okay, so ideally, if the world was ideal and you had the perfect spin polarized tool, you might expect to see something like this. You tunnel into the end mode, you flip the magnetization of your tip, you get 100% spin contrast. Of course, the world is not ideal. In fact, STM is very non-ideal in some ways, but it gives us an advantage in doing this experiment. So I've been telling you all this time how we use STM to measure densities of states variation, right? But actually STM does its best to try to get rid of density of state variation, right? Because it tries to move the tip up and down to keep the tunneling current constant. And that's a principle by which STM operates. So if I gave you, say, a chain of magnetic atoms, and you had some, say, parabolic bands, let's say, very simple band structure, spin split, and you calculate the density of states of up and down electrons as a function of energy, it will look like you have some spin polarization. You might think STM would, and also then what you do is you, say, go into the topological phase and introduce superconductivity into this system. You would get up and down polarization. So the Shiba states would show up and down polarization as well. And the Majorana would show up and down polarization. Okay? So we set out to think about making measurements of this up and down polarization of all these states to see if we can find a way to distinguish between them, Majorana and let me just say that this polarization, of course, so this is your Majorana end mode. In this calculation, you come in the middle. There is no Majorana end mode, but the Shiba states show polarization. Now, STM does its best to cancel all these signals, okay? Which at the beginning may seem like a very bad thing. But it turns out that it gives us an interesting advantage. So if you start out with a normal state of such a chain, and if you just think about what STM would do, STM will take the signal from, let's say, 0 to some voltage and tries to make this integral the same. And it does that by moving the tip height up and down. So when it moves the tip height up and down, if you repeat the experiment that you do in the lab, which is you measure the conductance with the tip, say, parallel or anti-parallel, you see almost no contrast. Okay? Does that make sense? Of course, there is one tell, which is that you can measure your tip actually has changed height. Okay? So you can then ask the question, what will happen if I do this experiment on these chains in this topological phase? Well, the same kind of thing happens. You have, let's say these are density of state measurement at the end of the chain. There is your Majorana zero mode. And there's your Shiba states. These are up and down density of states. Again, the STM would try to cancel this out. But you see, there is a difference. If you're in the normal state and there is no energy-dependent spin signal, okay, this becomes completely boring, the difference between those two curves. But if you have an energy-dependent spin polarization, there are actually small differences that plays a role in this measurement. Okay? So you can try to see if you can amplify that. So let's just look at, this is the density of state would be at the end of the chain. This is what the dIdV would look like. The difference would look like this. And now this difference starts to tell you an interesting piece of information. It shows that the contrast for the Shiba states, when a Shiba state is, let's say this is a magnetic chain and the chain is pointing up. This state is polarized up and this state is polarized down. Okay? What I mean by that is relative to the background. So you have a ferromagnetic system. Okay? You're making an excitation, a quasi-particle excitation. The quasi-particle excitation you make, you can basically figure out, what's its spin, average spin property. And the one above and below the chemical potential, when it comes to Shiba states, would have to have different, spin polarization. So now, and we have done this also now, you imagine you take the Shiba state to zero energy. The contrast basically goes away. So this goes back to a question I think somebody brought up, this band crossing. So the only way you get a Shiba state at zero energy is if you have two of them. Remember, Shiba states always come in pairs. So if I have a state at zero energy, it would be two states, not one. Okay? And basically you have both spin up and spin down. So if you find the zero energy state that has spin contrast, that's a Majorana. Okay? Let's see, what else do I have on this? So this is just the middle. So essentially, this is the experiment I'm going to show you we actually have done. Is basically look at what the spin contrast looks like of the Shiba states and the end states in the middle of the chain and at the end. All right. So this was technically quite difficult because we had to make tips that basically remain ferromagnetic with no field applied, but they were not magnetic that much that would disturb the superconductivity underneath our sample. A lot of finesse. But you can sort of see it works. You can just use the chain as a calibrator of the tip. You see this is plus 0 Tesla, minus 0 Tesla. So you can train the tip. Right? So you can put it in the up state or put it in the down state by applying a field, then remove the field. It stays in that up or down state. And then you can use this to do not just spin resolve measurement, but energy and spin resolve measurement. And again, when you do this tunneling measurement where you say, okay, keep the tunneling current constant, or you can see that with the parallel and anti-parallel tips, you're actually measuring a slightly different height. So this is a cut in the topograph here, which shows you how much the tip has moved up and down when you just flip the magnetization of the tip. Okay? So this is the cancellation effect that I was telling you about. So what we do here is we first remove superconductivity. Okay? When you remove superconductivity, you basically have these flat lines that I told you about. Boring signal, no gap, no Majorana state or Shiba state. Then you make measurement with one tip orientation and the other tip orientation. And if you do that, you find that the tip is at a slightly different height. Okay? About, I don't know, 50 picometers, but you can measure it. And you look at the spectra and you see basically very little difference between the up and down. Of course, the wire is magnetic, but you have canceled this magnetic contrast by measuring the current at a slightly different height. You've translated the change in current into reducing your tunneling strength. Now, so now let's remove the field. Field is 0. Wire, the tip can be trained up or it can be trained down. And you can go through and make measurements of all these features, the zero bias peak, the zero mode, the Shiba states, and of course the superconducting background. So you can see clearly there are differences in the spin contrast of both the zero mode and also the Shiba state. You can see it in just the conductance maps. Okay, so these I showed you about how we at these these higher energy resolutions and also better spatial resolution, you can have a tip up or a tip down, and you can sort of see the contrast just in the raw data. These are on the same color scale. Okay. And this is now basically comparing to what we expect from theory. So our Majorana has two eyes, left eye and a right eye. And that's where you see the zero bias peak very strongly. If you're in the middle, you see it, but it's not as prominent. This is a raw signal, up tip, down tip. Okay? And this is the raw signal for the Shiba state, up and down. So now you see, if you go in the middle of the chain, you have no zero bias peak. You have up and down. And you can see that the contrast between this state and this one reverses, just like we expect for the Shiba state. And when you go to the end of the chain, you see that there is this peak. Here on this eye is not as strong, but it's clearly there. And you can kind of see that even the Shiba end modes, which are slightly different than this one, also show the up and down. This curve doesn't show it as clearly. It shows very good down, but the signal to noise is very, very, very not as great in this data. So this is how we think we are basically setting a new piece of information, which says that this state, which is at 0, it has just as much spin polarization as a state very far away from 0, if not more, okay, relative to the background. Okay. And this is kind of what you expect to see if you have a true spin polarized state at the end of the chain. Right. So here, these are comparison to this. This is just our theory right now. We're trying to see if we can refine it. So what I'm plotting here is what we call the spin asymmetry. The measurement was done at zero energy or as a function of energy with the tip up, then the tip down. You subtract the two measurements and divide by the sum of two measurements. This is kind of a typical way. But it's all in the raw data. Okay, I'm done. So where is this field going? Well, hopefully we'll finish these measurements, but 2D. Can we make 2D structures which have P plus IP superconductor? Same principle. Ferromagnetic layers, strong spin orbit superconductor. In fact, there is a paper which I wanted to put on here, but I forgot, which actually with cobalt and lead, they may have built such a structure. It was just posted online, a group in France. I think I've worked on I still work on correlated superconductivity. See, in that field, we try to make exciting superconductors by finding exotic interactions. Here, we're trying to make exotic superconductors by cheating. We use S-wave superconductors, interesting band structure, and use proximity effect. And I think that there is a lot to do here in this space. There are some very nice papers out there which looks at the phase diagram of these 2D systems. They're chiral superconductors which are quite rich. And of course, the holy grail is not just to show that they are there, but to break them or show that they have non-abelian statistics, which I will stop there. Yes. Yeah. Yes. So we have some data on chains that are, so remember they grow out of this blob. So we have chains that are short and they don't show zero modes when they are very short. How short? 30, 40 angstrom short. These are like 200 and above. But, that also points to one of the future directions to try to create them by hand, build things atom by atom. But we haven't done that carefully. Yeah, we don't have enough data to really do that. They're going for optimizing growth and getting the longest chain. But on another project, we are trying to port this over into a superconductor where you can manipulate the atoms. Yes. No. I think once the idea is that once you could do this, which is on every freshman physics book, right, on top of a superconductor with a known spin texture, then you can do many things. Yes.
Directionality of that set by.
Well, in that case it is, but if you could do this, you can build a lot of complex structures, T junctions. Many things can be done. And the nice thing here is that the theory is, you can trust it. It's not a single particle physics, most of it. Okay, terrific. Hi.
I actually had another question, which is, we expect the Majoranas to be split from zero if their wave function had
Overlaps, yeah.
But also, I would think the fact that you have in-gap Shiba states would also couple the Majoranas.
No, it doesn't.
Okay, why doesn't it do that?
Well, basically because it's they are not they're in a different sector. They don't couple to other states. They are, okay, you got to think of the Majorana operator. Okay, if you try to, you can move electrons through it, but you cannot hybridize it.
Oh, I mean, I would expect the fact that you have sub-gap states throughout the wire would couple the Majoranas on either end.
Okay, through poisoning you can. If those states basically tail into zero energy, then that gives you poisoning, that gives you coupling. Yes, that's right. So you can put some numbers in. You can say, okay, I got a chain, they're this far apart. I calculate the overlap of the wave function.